Hello everyone, today we are going to talk about advanced routing features. During this process, we will discuss recursive routing. Recursive routing refers to some recursive search processes within our IP routing table. For example, if I want to find 30.1.2.0, we will use a static route like this. How do we find 30.1.2.0 through 20.1.1.3? Here we might be surprised as we are referring to 20.1.1.3, but is it on our directly connected route? It seems not. If my routing table doesn't recognize this route 20.1.1.3, I would consider it unreachable. And thus, this static route would be deemed ineffective and wouldn't be included in my routing table. For example, if I tell you all here, if you want to find someone, if you want to find Jackson, here you need to first find someone named Lao Zhang. Then you might wonder, who is Lao Zhang? You need to go through Lao Zhang to find Jackson, but in your view, you don't know Lao Zhang at all. So this matter to you is as if it wasn't mentioned at all. Suppose I now tell everyone. Classmates, if you just find a place where the entire room is made of gold, then you'll be rich. You would only think that I'm talking nonsense, because you know that you simply can't find such a place. So it's the same thing. When you tell it to go to this 20.1.1.3, and then you'll find 30.1.2.0, it will first question whether it knows it. If it doesn't know it, then asking it to find it through it is impossible. So here, we need to look at the routing table. For instance, if at this moment in my routing table, for example, right here, I first wrote a route to 20.1.1.0. Then who should the next route be for? I was startled. I gave it to 10.0.0.2, which means I gave it to RTB. Then I wrote another route to 30.12.0, and the next one is 20.1.1.3 site. Now, after I finish writing this route here, it will think about putting it into my routing table. It will first check, am I familiar with this next hop? It sees that I just wrote such a static route. It says if I want to find 21.21.0, I need to look for 10.1.0.2. Now, in this context, if I want to find 30.1.2.0, I first look for 20.1.1.3 and then I check. To find 20.1.1.3, who do I need to find? I see that I need to find 10.0.0.2. So, in this process, my RTA realizes, actually, the route I'm always looking for is 10.0.0.2. So, in this context, no matter what, if I want to find 20, 1.10 or 31, 2.0, I will find them all through it. This is equivalent to saying that now in this context. Let me tell you, if you want to learn about security knowledge now, you can listen to a teacher named Teacher Dashu. You might say, I don't know Teacher Dashu. That's okay. You know me, I'm Boya. So in your routing table, you'll know, if I want to find security courses, what about now in this context? I want to find Tree. I want to find Teacher Dashu. But who should I find first to find Teacher Dashu? First, I need to find Teacher Bawai. Then you can go through me to find our Teacher Dashu. This is the same principle. And here, this is called recursion, meaning I use this intermediary person to find the next person. In this context, this is our route recursion. Besides this, we also have an advanced routing feature here called equivalent routing. This means that in our IP routing table, if I learn a route through the same protocol, and its prefix and mask are the same. Besides this, we also say that in this context, our cost values are the same. Now, in this situation, I would consider it an equivalent route, meaning I can use this route to reach 10.0.0.0 per 30, and I can also use this route to reach 10.0.0.0 per 30. Both are reachable. Now, in this context, it's actually about comparing protocols. If I can't determine which protocol is better, I compare the cost values. If I also can't determine which is better based on the cost values, then at this point, I will form equivalent routes. This means that if they reach the same destination, from the same source, these multiple routes have the same cost value. In this context, we have different hops. These routes will be treated as equivalent routes and will all be placed in my routing table, meaning I can choose any one of them to reach the destination. These two routes are equal, and within this context, it will use its internal algorithm to select one route for forwarding. If during this process, we do not want it to form such equivalent routes, what should we do? For example, in this context, equivalent routes are like having 4 devices here. When these 4 devices are calculated through my device, it will rotate the routes for them. For instance, when this device here tries to find the 10.0.0.030 network, for example, based on my algorithm, I choose for it to go upwards. When this device comes over and also wants to go to this destination, I choose for it to go. When the device below comes, I also choose upwards. When this device comes, it goes downwards. If there are many devices, you will notice that both routes will be chosen, distributing our traffic. The load over these 2 links. Now, if I usually want it to take one route and use the other as a backup, then we need floating routes. Here, for our static routes, we can set different priorities here to make it prefer one route. Here we can configure the same source and destination addresses for it. In this context, we can configure the same destination address and the destination's wildcard. One route goes to RTB at 10.1.1.1, and another goes to RTC at 10.1.2.2. However, here, I want it to prioritize RTB with our RTC as a backup. Now, in this context, we can set the priority for it. Priority, the default priority for static routes is 60. So this one is 60 and this one is 70. When it is placed into my routing table in the future, it will consider and compare their priorities. In this process, the smaller the number, the higher the priority. So we will choose the one with 60. As a result, the route to RTB will become the primary route, while the route to RTC will become the backup. This way, we achieve a backup for the forwarding path. We can also refer to the backup route here as, for floating routes, only on my main route. That is to say, if one day, alas, I usually take this route, but one day it has a problem. For example, it shuts down. Or suddenly, I can't perceive the device on the other end of this link, then at this time I will be startled by this main route. When I consider it unreachable, my routing table will switch to this backup route and take this RTC. In this way, we can achieve a switch. For example, let's take a look at a case here. Now, in this process, if within this, when our RTA and RTB, if the link between them is normal, then in our routing table, the next hop is written as 10.1.1.2 with a priority of 60. Now, if during this process, we also wrote another one with a priority of 70, since 70 is not better than 60, it will not appear in our routing table. Only the one with a priority of 60 will appear in our table, and RTA will send the traffic to 10.1.1.2. Now, if the link between RTA and RTB fails, then we won't be able to reach it as before. The next hop of 10.1.1.2 will lead to this path being ineffective. Yeah. Earlier, someone compared us, one was 61 and the other was 70, but now we lost the comparison, so we won't appear in the table. However, now the one with a priority of 60, because the next hop is unreachable, doesn't even qualify to be added to the table, so it's just me. And at this point, we definitely don't need to compare. It will directly form a routing entry and be placed in our routing table. Here, we will find RTC, and through RTC, locate 20.00.00, which is our floating route. This means I can set it as primary and secondary, determining which path it should prioritize. Besides this, we have another technique here called CDR. Previously, I talked to you about VLSM. Variable length subnet mask involves shifting our wildcard mask to the right, I, whereas here with CDR, it actually shifts the wildcard mask to the left. It reduces our network bits and increases our host bits to expand the range of the subnet. In this context, CDR uses IP values and masks to identify our network and subnets, including our hosts. CDR replaces the old classful network design, such as Class A, B, and C. So CDR is actually based on variable length subnet mask, VLSM. It uses prefixes of arbitrary lengths to divide the address space with continuous IP addresses. In this context, I aggregate them into a single network, which can effectively reduce the number of routing entries. For example, in this case, we have these routes, 12.0, 10.0, 9.0, and 4.0, these 4 segments. I can aggregate them into 192.1, 168.8.0 to 11. At this point, the routing entries in my routing table will be greatly reduced, optimizing my routing table and my routing entries. Now, in this context, we talk about subnetting and VLSM, which address the issue of address wastage. However, they also introduce a new problem. As I divide the network segments, the number of segments increases, leading to more and more routing entries in my routing table. Here, we can use route summarization to optimize these routing entries, reducing their number. Here, if RTB wants to find 1.0R, 2.0, 3.0, 4.0, 5.0, and 6.0, it must have these routing entries. If we configure static routes for each network segment, then the workload will be very large. Moreover, in RTB's routing table, there will be a large number of such routing entries. In large-scale networks, if routers or other routing devices might need to maintain a large number of routing entries, it will consume a lot of resources. Additionally, if the size of our IP routing table keeps increasing, meaning the number of routing entries continues to grow, it will lead to a decrease in the efficiency of routing entry lookup. Therefore, we need to optimize the size of the routing table here. At the same time, I need to ensure that the router can reach different network segments. If I can appropriately plan a network segment, we can use different methods to achieve summarization. This is called route summarization, also known as route aggregation. How do we aggregate? Here, route summarization involves combining the same routing prefixes into one. For example, let's give a simple example here. They all start with 10.1.1.0. Here, this is the IP segment of 10.1.1.0. Besides this, for example, I also have 10.1.2.0, 10.1.3.0, and so on, up to 10.1x.0. I currently have so many routes, and they all actually start with 10. 1.0.16. So now here I can tell RTA that whenever it needs to find this 10.1.0.16, I can direct it to whom? Direct it to RTB. Now, in this process, route aggregation involves combining routes with the same prefix into a single route to reduce the number of routing entries in my routing table and improve our efficiency. Route aggregation uses CIDR technology to combine network segments with the same prefix into a single network address. Before aggregation, these routes are referred to as detailed routes, and after aggregation, they are called aggregated routes or aggregated paths. Now, for example, with our RTA, I arrive. This destination network segment clearly has several addresses, like 102, 103.0. So what about them? They all have the same next hop. Therefore, here we can summarize them into a single address, meaning whenever I look for them, as long as the network segment is 10.1. At 0.0, I can send them all to this RTB and let it help me forward them. This way, it reduces the size of the routing table on RTB. So, how do we calculate how much to summarize it into here? For example, right here, we have 192.168.1.0, 2.0, and 3.0. Now, in this process, we first need to convert them into binary numbers. So, after we convert them here, for instance, what do we do next? Here, we need to find out from which bit our IP address starts to change. All the previous bits are the same, and from this bit onward, it could be 0. It could be 1, or it could be 0, again indicating a change. Now we copy down the previous bits and convert them into decimal. As for the bits that follow that, they are all set to 0, regardless of whether they are equal or not. we all categorize it as 0. Now, in this process, categorizing it as 0 means it's like this now. And then we convert it to decimal, which is 192.168.0.0. As for how this calculation is done, how is it calculated? We need to see how many identical numbers there are. This one is 8 bits. This one is 8 bits. 2 8s make our 16 bits. 17, 18, 19, 20, 21, 22. There are 22 identical numbers. So here, we use 212 to represent the length of our summarized mask. This is our root summarization. You might ask, what issues can root summarization optimize in our routing entries? Well, it does have certain drawbacks. For example, during this process, in this diagram, if our RTB receives a route indicating that the destination network is 10.120.024, and then in this situation, I will check my routing table and find that I have a default route. If I don't recognize it, I will send everything to RTA. Now, in this case, it will send these routes to RTA. Once RTA receives them, due to our route summarization on RTA being too broad, it causes RTA to think. Anything that starts with 10.1.0.0 is considered to be on our RTB, so it will think that 10.1.20.0 is also on our RTB. This is because our summarization is a bit too broad, causing you to claim you have something externally that you don't actually have. In this case, it will use this summarized route in the routing table. Forward it to whom? Forward it to RTB. If it can't find me, I can't find it. This is a blame-shifting behavior, like saying, hey, I pass this problem to you and you pass it back to me, which creates a loop. So in this context, if we configure such route summarization or configure such missing routes, we need to be careful. Now, if we want to solve this, how do we go about it? In this context, we need to create a black hole route, which means, if in the future I want to go to this static route, which is 10.1.0.0.16, then I will throw it into the black hole route. A black hole route is one way preventing the occurrence of routing loops during route summarization. We say routing loops are here, and in most cases, we need to connect static and dynamic routes to an exit. This is connected, and this interface is the one that connects the device to our destination network. In our routing, the exit interface can be a physical interface or a logical interface, such as a virtual interface. If it's an alarm in this context, this is a logical interface that is always in an active state. This is similar to a black hole, where all incoming data will be discarded, as if thrown into a trash can, thrown into a black hole. Therefore, this is referred to as a black hole route. Now, in this process, if I want to go to in the future, this 10.1.20.0. Now, in this process, what about my routing table? I don't have it. I will still pass it to RTA. Now, in this process, because our summarized route is too large, it thinks that anything starting with 10.1xx can be given to RTB, as it has all of them. Now, in this process, because of this, it writes such a black hole route. So after it arrives, it won't create a loop, but instead, this device will discard it. Here, if in the future, this RTB, consider the route. On him, for example, there's this 10.1, 10.0, then RTA, it will still. In the future, when looking for this 10.1, 10.0, it will be sent to RTB because he thinks. In this context, as long as I look for 10.xxx, I will send it all to RTB. Here, because we say its routing table also has details besides the details, there is also this 10.1.0.016. If I can match both of these routes in the two routing tables here, but because of the longest prefix match principle, I find there is such a detail, I will prioritize choosing the longer prefix. Therefore, in this context, I can normally forward what is in our routing table. And for what is not, I will directly solve our routing this way. Routing loops. Well, here, besides this point, of course, it is best to perform precise route summarization. When we are doing route summarization, during this process, we can observe On RTB, there is 172.16.1.0 to 172.16.31.0, and on RTC, there is 172.16.32.0 to 172.16.63.0. If we, like before, casually perform a summarization directly using 172.16.0016, it will lead to, in the future, when I go to 172.16, regardless of the specific address, I will provide it. The key issue is that on RTB, there isn't, for example, 32.0, 33.0, or 63.0. So if we configure the summary route like this, it will include these subnets. Therefore, this will cause RTA to send packets, which should originally be sent to RTC, to the wrong subnet. Sent to RTB, this will lead to data packet loss. This issue is caused by our imprecise route summarization. To solve this problem, our route entries for summarization must be precise, meaning they should only cover all the specific routes that need to be summarized without including additional routes. For example, if we want to perform a summarization in the future, here we want to summarize 172.16.10, 2.0, and 3.0. Now, in this process, we convert them into binary, and then compare from left to right. Here, we can see in our current network, up to this step, up to this line, everything before this vertical line is the same, so we copy it down as 172.16. Then, after this vertical line, we set everything to 0, and converting back to decimal gives us 0.0. Also, we see how many bits are the same, which is a total of 12 bits. In this situation, to ensure it is indeed correct. It includes all of this without any excess. We can calculate its network address and broadcast address. That is to say, the smallest address is 172.16.00, and the largest address is 172.16.3.255. This exactly fits within this subnet range. Meaning, when we summarize here, it's best to summarize accurately to prevent having routes that we don't actually have, but because of summarization. What happens if the summarization is too large? It could lead to unnecessary routes being forwarded from our path, which is not good as it may create a risk of loops, or the risk of route drops. Here, you should know that this is our route summarization. If you want to learn Huawei certification technology, or obtain Huawei certification question banks, please send me a private message, or you can leave more comments below the video. For technical exchanges,